So I guess we might as well get going. My name is Rich Graham. Doesn't say it on the slide.
You remembered it anyway.
Yeah. I'm in the architecture group at Mellanox. I focus on HPC. And what I'm going to talk about is what we're doing as a company looking forward to guide our way towards Exascale. So first of all, historically, or currently, we have a large presence in HPC. There's some statistics here from the top 500. The number one machine in the world in China is using our silicon. They've managed to achieve very high rate of performance, 93 petaflops. 3 times better than the number 2 system in the world, running a very large number using a very large number of nodes, 40,000 nodes, large number of cores, 256 cores per CPU, and as I said, it's using our silicon for the interconnect. So overall, also, if you look, there's statistics here in terms of our presence in the top 100, top 200, etc., the different tiers in the top 500, and as it shows, and it's well known, we have a large presence there.
So you say your silicon, you're talking about the HCA itself, or it was like embedded silicon somehow in the board, or?
They buy the parts from us and use them. Right.
They didn't disclose whether those were InfiniBand parts or Ethernet parts. We all assumed they were InfiniBand related. Is that network truly InfiniBand, or is it some sort of hybrid?
So all we can really say is what's been publicly announced. Even if you notice, even our announcement came after things were publicly disclosed by others.
I noticed.
Yeah, so
okay.
We can't say anything about that. I'm sorry. So also, as folks know, historically we've had a big presence in HPC over the years in several very large systems. The most visible ones these days are the 2 that were bought as part of the Coral procurement for Department of Energy in the U.S. with a platform at Oak Ridge called Summit, and one at Lawrence Livermore called Sierra, scheduled to be deployed next year. These systems have been important for us in terms of helping us move our technology forward towards Exascale to meet some of the challenges there. And as the need for performance has kept growing over the years, so has the technology associated with it. It too has been evolving for a variety of reasons. Those of you that remember, the big thing in the late 90s, early 2000s were large SMP clusters. The SGI origins were probably some of the best examples here. So the focus there was really on clusters. Then, as clocks slowed down, the variety of single core and many core systems have become a lot of what we use today. And what we view moving forward as the next step here. If you notice, these really focus a lot around how the CPU is used. We believe that the next step forward will come as part of co-design of systems, taking into account application needs, hardware capabilities that can be provided, as well as software capabilities. And this is what part of what this talk will focus on. So we support what we call the intelligent interconnect. We believe this is the right way to move forward. If you have a CPU, with a CPU-centric type of approach, which is the approach used often today, The CPU is really the center of the computation, of the simulation, I'm sorry. And so everything that happens is focused around, or a lot of what happens is focused around the CPU. Data needs to be brought to the CPU before anything can be done with it. Data is sent out from the CPU, and so the CPU is doing a lot of things more than just doing the computational part of the workload. It's doing a lot of management too. And so in the move towards co-design, the intent here is to move as much as possible, as much as makes sense, of the management of system activity in support of the applications away from the CPU and into where it makes sense. So we do a lot. We build networks. So we look and try to understand what we can put within the network, and what can we do with data as it's moving through the network to increase overall application efficiency. So that's really our focus. As you know, we're also starting to do that a bit with storage, assistance for storage, with some of the NVMe support that's been talked about. So this is really a direction that's important for us, and we put a lot of thought into trying to understand algorithms, and trying to understand how, if there's an appropriate way to map these algorithms in a better way onto the system. So to explain part of the reason why this is relevant, why this is important, it's useful to look at the trends in terms of latency is one component, how it's evolved over the years. So on the order of a decade or so, we were still talking about hardware where network latencies. So we focus on latencies not just because it's a fun thing to do, but many HPC applications are very latency sensitive, which should be a comment that should go in there. So on the order of a decade or so ago, the network latencies were on the order of 10 microseconds, and the communication libraries added their latency to it. So there's a reasonable latency penalty to getting to the network, and therefore for the applications to be able to continue computing if they're waiting for communication to complete. Today we're talking orders of a tenth of a microsecond or so in terms of the overhead that's added in accessing the network. So this overhead is really what's listed here is the cost of the HCA itself actually adds. Of course, there's a cost of getting into the HCA and the like, but these costs have come down a lot. And really in reality, there's not much more to take out of it. Hardware takes what it takes. You have data moving through the network. The communication fabric framework latencies have also come down. These numbers are actually lower than 10 microseconds. It depends on what sort of operations you're talking about, but they're getting to be low. And so there really isn't a lot more to be taken out of, to be moved out of in terms of latency removed from the system. There is some, but the big pieces are gone. And so really from a holistic point of view, you need to sort of look and see how the system is used, and see what's the next step that you can take to continue and get big performance enhancements at the application level.
So what's the approach here, just from today to the future, gaining from half of the latency, from 0.1 to 0.05? I mean, what's the main co-design that will be changed in the future?
So this is not part of the discussion of the co-design. This is the motivation for co-design. Okay. So you're going to reduce it by, if we're lucky, by 50 nanoseconds or so. And the point here is that that's good. We want to do that. We'll continue to do that, especially as network people. We want to drive everything to zero, all latencies to zero, always. But look at your application. That's not going to impact your application a lot. It will help. Of course, everything less is better. what we're looking for are things that will have larger impact on the application. And therefore, it's really important to understand what sort of characteristics applications have in terms of their communication. There's some very easy targets up front, as everyone knows. Collective communication is in use broadly, for example, but there are other patterns that are in use that people are trying to understand and see how those can be mapped to the network. So that's really the point here. So, yeah. Some of these features start to make themselves better known in hardware or EDR hardware. So switch IB2, which is out in use now, and Connect X5, the HCA that was announced at ISC. So this is where we have some new features that come in that really help in terms of this view towards looking holistically at a problem and trying to solve a system problem and not just a small end node type problem. And I'm not trying to say that the end node problem is not an issue. As I said, as network people, we always want to improve the performance at the end node. But we want also performance that impacts the application well. So in terms of characteristics of switch IB2 and Connect X5, we have with switch IB2 we introduced a new technology that we called SHAIP, called scalable hierarchical. I work on this every day and I've drawn a blank. SHAIP, yeah. Hierarchical protocol. Thank you, Scott. Sorry. And what this does is it moves the manipulation of or the management of collective operations from the end node, where data at every step needs to go from one end node to the other end node to the network. So basically, data goes into the network once, is manipulated completely while it's on the network, and comes out of the network with the answer. So it's sort of like posting a send. And when you get a read response, you get your reduction, the result of your reduction. So this supports, the hardware supports barrier, all reduce, and broadcast, although broadcast is not exposed at this stage. We support all the reduction operations that are defined in MPI and SHMEM. For 32 and 64-bit entities, both integer and floating point. What we do not support is the floating point multiply, which is not in much use at all. And it provides a large improvement in performance of these collective operations. I can't remember if I think I have data on that next. In terms of Connect X5, this is our second EDR HCA. The latency remains, this is verbs level, on the order of 0.6 microseconds, so really not a change in latency. Message rate goes up from about 150 million messages per second to 200 million messages per second. So for those applications so in a multi-core environment, this is very important, especially for those that send a lot of small messages. It does continue to support collectives in the hardware. We've had our Core Direct capabilities for quite a few years. Those are continued to be supported. We add to it support for MPI tag matching. So specifically, this is useful for being able to do, one can do tag matching and deliver the data associated with it to the appropriate place as the application is computing. And so there's no need to wait for the application to finish its compute phase, then try and manipulate the data, try and do the tag matching, and then all the associated communication with it. It's simply delivered as the application is being processed, is progressing at simulation. And there's also the addition of memory on the host channel adapter that's accessible from user space. So users can directly access it, and more important, control where it sits. So if you have data elements that are used frequently by a lot of different endpoints on the network, this is a natural place to put them. It also brings first-time support for PCI Gen 4. It has an integrated PCI switch within the HCA, and it now provides dynamic routing support at the end node for RC, reliable connected transport, and DC, dynamically connected transport, which is our scalable transport. So we have and had for many years support for adaptive routing in the switches. It works well. It's useful mostly for UD. Now this supports the full range of transports in terms of adaptive routing, and as another way to help improve application performance. A bit more about speeds and feeds here. So I talked about the performance of Connect X5. The switch is still a 36-port switch, under 90 nanosecond latency per port. Full bisection bandwidth in both directions, and actually it's measurable is very close to this. I mentioned already the message rate, 195 on the order of 200 million messages per second. Also, as part of the family, we have an Ethernet switch, 32-port Ethernet switch, which is also a 100 gigabit per second switch. Notice both the full line is backward compatible in terms of speeds. We also have a range of cable products, from copper to VCSEL to silicon photonics. And on top of that, since we do provide end-to-end solutions, we also have our software product, HPCAC, which supports MPI, OpenSHMEM, and UPC on the platform. So this is based on the OpenMPI code base with accelerations with point-to-point and collective acceleration engines that we add here. So a bit about how this all impacts application performance. So we have some performance data here for several applications. You can read them. You can read what they are yourself. We're comparing the performance of these applications using FDR InfiniBand and EDR InfiniBand. And generally what we see here is we see these are plotted as a number of MPI processes. Here, this one is plotted as a number of nodes. Anyhow, what we see here, and these are rather modest sizes. We see that even on 32 node systems, this is also a 32 node system, we see some significant performance gains from moving from FDR to EDR. And of course it maps into the characteristics of the application, how much they use large messages, and therefore how much they benefit from the increase in performance. There are other issues on the card, things we don't necessarily go into, where there's a lot more ability to support more communication in the card and the like. So overall, we see a very nice improvement in application performance, in the performance of these applications. Brief picture on the performance of SHAIP as MPI all reduce in the context of an application. So Mini-FE is one of the Department of Energy core applications. What we did is we actually, typically when you report performance of collective communication, everyone looks at OSU benchmark, IMB, or something like that, where everything is hot and cache. You run it, and it's the best you can possibly get. And actually, I'm surprised. I forgot I don't have that data here. What we do have is the application data. So what we did here is within the application, within Mini-FE, we measured the actual performance of the collective and compared it to the host-based collective and compared it to what we expect out of the SHAIP. And we see a nice difference in performance here. We are actually making measurements on full applications and looking at the impact of full applications too, using SHAIP. I don't have any of the data here, but we do see some nice performance gains in overall application performance for those applications that are using the particular reduction operations that are in use. So what I didn't mention is currently the limit on the size of reduction that's supported is 256 bytes. So anything beyond that, you either have to pipeline it, basically at the communication library level, you pipeline it, which is also very, very effective, even more than just a single collective of 256 bytes or less. Or if it gets too large where pipelining doesn't work, you have to go back to software-based approaches currently. Here's some data comparing the performance of SHAIP on a KNL machine using the OSU benchmark. These two bottom lines, green and blue here, are OSU and IMB latencies using SHAIP, and here and above them, these are the same measurements using a host-based approach. And it's not surprising that SHAIP performs much better than non-SHAIP measurements. To me, this looks like an anomaly here because the SHAIP-based approach beats the end node-based approach almost all the time, basically. Here's the same result for barrier, and we see the same thing that using SHAIP, these two lower points, outperforms the host considerably. And this actually, as the size of the system increases, this is expected to get better. Not just because you have an underlying system that by its nature is very low latency, but also one of the things that happens here is there's no contention when you use SHAIP. The data paths are well defined and there is no contention. Whereas if you on a host-based approach, you're to the mercy of where you happen to be allocated in the system and how your routes happen to be mapped. See, I need to speed this up a bit. Here is a bit more performance data on OpenFOAM using SHAIP. Using SHAIP and HPCAC, comparing to base OpenMPI and Intel MPI. All this is not Omnipath. This is Intel MPI running on top of InfiniBand. And we see that SHAIP, as well as some other accelerations, again here, make a big difference on OpenFOAM performance. So these sort of approaches for looking at the problem holistically are definitely are helping in terms of gaining performance. It's the same. This is the same underlying network. It's just are you looking at the problem holistically or not? That's really a different. Are you solving the problem holistically? Is more appropriate to say. So, for the sake of time, I'll speed on. But as I mentioned before, we really do provide a full end-to-end solution from the very low for communication, for networking, from the low-end silicon clear up to communication libraries in what we do. Briefly, we've announced a system on a chip solution called BlueField that is aimed at storage and SDN type of problems. This uses an ASIC that has integrated into it both ARM cores as well as the network. All these are on the same die. And this is, as I said, this is really aimed at storage solutions where it can be used to manage SSDs and the like, as well as packet processing for a variety of packet processing applications. This is an outcome of an acquisition that we made within the last year of a company that Easy Chip that did this work. So we're looking at other ways. This is one of the other another problem to solve in terms of moving management away from management of these sort of activities from the host to a component on the network. The other capability that we've released this year and are continuing to work on developing it is our support for the InfiniBand router. So this is what this is a router that's embedded in our switches. The router can support up to 6 different subnets simultaneously. Everything here is managed by the switch. All the routing is managed by the switches. Latency added going through the router is up to 50 nanoseconds, if I remember correctly. So very low penalty for very low latency penalty, and it basically lets you isolate, do your typical system administration type of isolation. So you can build a compute system and a storage system, both sitting on separate subnets. And you can use RDMA to transfer data between the systems, and you can obviously have a file system that supports multiple compute systems. As I said, the current restriction is a given switch or a given router can only support up to six subnets, but this is changing. This is going up. So you no longer have to play all sorts of, it's much easier. You don't have to play so much games trying to make sure that your compute fabric, for example, is a fat tree, and when you want to add storage to it, you don't somehow break that topology, or you don't have to use routing chains, which is another mechanism that was developed for this sort of thing. And it gives you much better system management capabilities. The additional feature that was added that we support now, starting with ConnectX-4, actually, is the multi-host socket direct approach, where two sockets, they don't have to be on the same host, but for the multi-host, by definition, they are on the same host. Two sockets can have independent paths to the HCA, and so they don't have to. So data going from data destined for this CPU, for example, for this CPU does not have to go through the internal CPU network, their memory network there, and so this helps a lot in terms of latency, and also obviously. Helps reduce the amount of CPU usage for these sort of data transfers, and so this is one way to improve system performance is by using multiple CPUs connecting to the same HCA. Let's see. So let me talk. So one of the other things that we do, one of the other technologies that we support to improve system efficiency is the GPU direct capability, the ability to transfer data from one GPU to the other GPU over the network, not necessarily needing to go through the CPU. We can see some performance numbers here for HomeD, where there's significant performance advantages for using GPU direct as opposed to not using GPU on this system. To get a bit more, we also see another graph of the improvement in latency as well as bandwidth using this data. So this is data, the work that was done by DK Panda and his group at Ohio State. So we see that this sort of support really helps tremendously improve the system utilization for GPUs. A bit We also have the same sort of information. Here again, I don't know why we have this slide twice. I want to get to the next slide. This talks a bit about a bit more about the history here. So GPU Direct support for GPUs, I should say, is technology that's evolved over time. It started early on by just allowing GPUs to access the network with the assistance of the CPU. So both data as well as control path all went through the CPU. Then it came to moving the data path to actually step 3 involved moving the data path to be independent of the CPU, so only control went to the CPU, goes to the CPU. This is what's known as GPU Direct RDMA, which is in use today. So here, the CPU prepares, does the control operations. It prepares the work requests necessary to send the data, and then once the GPU has the data ready, the GPU itself does writes the doorbell basically and gets the data out of the network. So again, here the data path no longer goes through the GPU, and now GPU async, not sync. This is a typo. Also is the work there is going towards moving both control and data path directly to the GPU. So the CPU is no longer necessary in this operation. So it makes it much more tractable just to run full applications on the GPU, and not worry about the CPU. So this sort of capability is very important to NVIDIA with their deep learning capabilities. They have a system that uses EDR as the interconnect between their GPUs, and it's, as I said, it's used in deep learning. So a bit more getting back away from describing details of what's supported and the like, a bit more into higher level view of onloading versus offloading. So to define the terms first, so an offloading approach, as is obvious from the name, what's done is as much as possible of the control path is moved from the CPU is moved away from the CPU to the HCA, to the switch, someplace else, with the intent here of letting the CPU focus on what it's doing, what it does best is really do computation for the simulation. It's very good at doing floating point work and the like, and so we want to free up as much of the resources as possible to be able to do that, and also allow for communication to progress independent of computation. Whereas the onload approach, it really, what it does is it uses the CPU for everything, basically, or for most everything. And so the CPU is involved both in simulation, progressing the simulation, as well as management of what's happening everywhere else in the system, be it the network, be it the I/O system, or anything like that. And so these are fundamental differences between the two. Now, in terms of the offload architecture, this requires, this requires a lot of thought, a lot of investment. We're putting a lot of investment into it ourselves, and you'll see stuff coming out in the next several years as a result of this. But there's a lot of work here to try and figure out what makes sense to put out to the network, and what doesn't make sense to put out on the network. So the obvious things have been done for 15 years, since the inception, just management of your queues and the like. But as I alluded to, other things are being moved to the network. Whereas with the onload architecture, you continue with things as they are, and the like. So there's an interesting paper came out of Sandia, National Lab, as well as UNM, University of New Mexico, comparing specifically the approach of offloading and onloading. And for those of you that are familiar with the folks from Sandia, as well as folks that used to be at UNM, they're big believers in offloading of communication management to the network. And so what they did here is they did some simple measurements of network performance as a function of CPU latency, I'm sorry, CPU speed. You can see the speeds here running from 1.4 gigahertz up to 3.8 gigahertz for the onload approach, and then comparing the same thing also as a function of the same CPU speeds for the offload approach, where most of the management of the activity is happening off host. The interesting thing here is the speed of 1.4 gigahertz is above where KNL typically runs. And so what you see with simple operations like this, just a put operation, it's harder to get simpler than put, that there's a big impact on performance and therefore on the application when the CPU, when a slow CPU is used to manage, to handle the put operation. The offload approach is essentially almost insensitive to it because there's almost no work done on the host. You have to initiate the traffic, you have to check for completion and the like, but everything else is done in the network independent of the speed of the CPU. So this is a real demonstration of how those sort of approaches can impact application performance. Of course, it always depends on how much communication the application actually does. See, I have.
We also have some data on the amount of cores that is being used for communications on a single HCA. We only talk now about frequencies, but it can differ a lot whether you are using, let's say, 12-core CPUs or 18-core CPUs.
So remember, things that happen on the network are very different in nature than what you have in the CPU. So on the network, you really don't talk. The issue of cores is not really that relevant. It's not totally true. The hardware itself has a lot of parallel paths. So of course, there's parallelism in the hardware. There's no doubt about that. The point here, and I mean, anyone that builds a network can tell you that you can't achieve the high message rates that everyone gets if your network has, for example, one thing that pushes data through the network. There's definitely parallelism there. The point here on the communication is that because the processing is being done by the HCA, it's insensitive to what's happening on the host. So yes, if you take the HCA and run it at half the speed, of course things will be slower, but that's not how things are done. Okay, the CPUs are run at different speeds, and those different speeds do affect the way simulations are done, and so that's what this is demonstrating.
So is this true also for the message rates? I believe when I tested the message rates, I've seen that the frequency of the CPU just made a lot of impact on.
Yes, because you have the initial part. So the hardest part in a message rate, if you're doing an MPI message rate, the hardest part in an MPI message rate is not what happens in the card. The card can sustain this. This isn't an issue. It's how long it takes the software to set things up.
Yeah.
And so if the slower the CPU goes,
then the message rate.
that's right. And it's just the way things are. I mean, yeah, that's all. Yes?
Do you have any similar figures or idea on what happens on latency?
This wasn't our.
This was bandwidth, if I'm not wrong.
Yeah, so this wasn't our work. This is what they did at Sandia. I don't know. I'm not going to guess. I can guess, but I mean, we just said things get a little so. But I don't know. They didn't. It might be in the paper. I don't remember what's in the paper. Look, it's published. It's a published paper, I think. If you can't find it, let me know, and I'll get it for you. It's not an issue. Here we also have application performance as a function of a comparison for LS-DYNA of performance using again the offload versus onload approach. So there's a 100 gig proprietary network versus EDR InfiniBand. These were measured on the same host, these were measured on the same host. And we can see that EDR for this test case is performing considerably better, so higher is better than the proprietary interconnect. So these are two different LS-DYNA values, and you can see in yellow here the performance in terms of percent, the performance difference between the two runs. And here the difference between the two is the interconnect that's used, and of course the MPI that's used. So we can see that this offloading capability really does help here. We also have results for spec MPI. Sorry, that's a benchmark that uses a variety of applications and puts them into a scoring system to report a single number. Here we have the performance for several of the components in this measurement. I'm guessing it's 32, it's 1024 cores, so it's a 32-node system using a Xeon processor, Intel Xeon processor. And again, here we can see that for these applications, ADR InfiniBand, this is ConnectX-4, not ConnectX-5, performs better than the other 100 gigabit per second interconnect. So we do really see benefits to moving application benefits to moving processing of communication to activity to the network. They also have a measurement, sort of a follow-on to what Dan talked about earlier today, which unfortunately I missed, but.
Very, very good. Extremely good.
I'll second that one. Comparing here basically different characteristics of performance of network characteristics when one is doing a very large data transfer. So this is basically doing, if I remember correctly, about 100 gigabyte data transfer and measuring what's happening in the system, different pieces of the system, and comparing InfiniBand to the third-party approach, and looking at CPU utilization. We see that CPU utilization with InfiniBand is very low. I mean, that's what it's designed to do. So there's no surprise here. The other interesting thing is the CPU frequency drops. That means the CPU is not busy. Whereas on the other, these again were done on exactly the same system, just two different interconnects connected on it. We see much higher CPU utilization to progress communication, as well as the CPU frequency not dropping. So we can see, I mean, this is designed not to use the CPU, this is designed to use the CPU, and so you see the differences in performance. And there's some other measurements here in terms of data throughput rates for InfiniBand and the third-party interconnect. Also, we see here, as I say, a summary of the same number, how the CPU frequency drops. Number of instructions, CPU instructions executed is also significantly less with InfiniBand, and the number of cycles necessary to actually do the operations also is considerably less. Again, this should not be a surprise because of the architectures. One is designed to work one way, the other is designed to work another way, and these are results that one would expect. So, in summary, we're at 100 gigabit per second at this stage. 200 gigabit per second networks are just around the corner next year. We see already today a good competitive edge in terms of performance for InfiniBand, EDR InfiniBand against other communication protocols. It shows up in a variety of both technical measurements as well as in APIC operational cost type of measurements. So I think that's it. Any? Yes.
quick question. Any plans for extending the subnet size beyond 64K nodes?
So it's less than 64K nodes, it's around 48K. The answer is yes, but not in ways that you would expect. So IB router, for example, is a way to do that. And so that's,
Always through the router.
for now, that's the way to do it. Most of the systems, so if you noticed, so I mentioned the penalty. I specifically mentioned the penalty for going through a router, because that's very relevant in these sort of circumstances. It's very, very small, and the other thing the other thing too is in your topology, any switch in the topology can be a router, so you're not suffering in terms of the sort of topologies you can use either. So, but there are very few. There are very, very few systems today that are larger than that, and we feel currently that we have a good solution for that. Yes?
So the question that keeps coming back about onload versus offload is that if you do blocking communication, then the CPU cannot do anything else than communicating. And therefore, if you use a CPU so that you do onload, then you can make a much cheaper card.
You can make a cheaper card. Applications would prefer, so there are definitely applications still use blocking operations, especially collectives. That's true. There's no argument there, but the applications have tried, and has sort of abandoned it for a while because hardware didn't support it, have tried to do asynchronous communication. The MPI standard is certainly making it easier to do that. I believe the SHMEM standard will make it easier to do that. You're right, there's no argument there. You have opportunities with the offload approach that you don't have otherwise. I mean, you have when you do things on the data path, you can do things that will impact performance significantly than if you don't use it. So yes, you can maybe build cheaper cards. I don't know about the cost of economy, but I stay away from that. So.
Okay.
Thanks.